Okay, we're going to do our last lecture online. And so what I'm going to start with is the equations that we're going to be working with, and then I'm going to talk about and do some examples of where each one is used and how it is used. So this is for our electromagnetism, so we're trying to finish up all of our info on electromagnetism, and this will be the last bits that we talk about. So if you look on your formula sheet, a couple of numbers that you're going to need to know here. The first one is the magnetic constant, and that's the one that we're going to need the most often over here. So the magnetic constant is sort of like the constant for electricity. It tells you how far the field penetrates or how strongly the field behaves in a certain region of space or inside an object or inside a tube. So the magnetic constant is mu sub naught is the symbol we use for it, and its value is 4 pi times 10 to the negative 7th. And that is in Tesla meters per amp. So this is Teslas, which is electric field strength, meters, and amp. So it comes from the magnetic field strength, the area, the meters, the distance that the field strength penetrates, and the current that is running through at the time it occurs. So it's similar to our electric constant, and our electric constant is K, and it is 9 times 10 to the 9th Newton meters squared over Coulomb squared. So it's very similar. Amperage is current, where charge, C is charge, so they're both referring to the movement of charges. They both involve the distance, although magnetism only needs a single distance, how far in, how far up, how far out, where the electric constant is more about an area of permeation or permeability, and then both depend on forces. So Tesla's is magnetic field force, Newton's of course is force, and so those two we use quite a bit. You will also see K written as, let's see, what's the other way you can see it? 1 over 4 pi epsilon naught, where epsilon naught is 8.85 times 10 to the negative 12th. We don't use that a lot. We don't write it like that in AP Physics 1 hardly ever. We use it more like that in Physics C because of the nature of moving through a field or moving through an object or things like that. So those are the first pieces out of the formula sheet, but the one you really want to concentrating on today is everything with magnetism, so the magnetism constant. Then if you scroll up, you'll see that there's a section entitled Electricity and Magnetism, and because I want us to work with some of these formulas, I'm going to point out some of the key ones. The first one is force magnetic is QVB, V cross B, which means it's Q times V times B times the cosine of the angle between them. And I'll show you how this, I'll illustrate how this works, but we use this one is a lot because this is the formula for finding the magnetic force. Come on, buddy. So just like we have an electric field force or a tension force or a buoyant force, the formula for magnetic force on a particle is this formula, okay? And you'll see it, if you're looking, you're going to see it down underneath all the letters and their names. It's going to be the first formula underneath that. So those formulas that you see underneath the legend for what letter stands for what value, that's the formulas we're going to be talking about here. So on, actually, sorry, I miscopied that. This is not cosine, it's sine. It is sine. So that's my fault. So you actually see it written twice, one like this and once like this. The other force that we're going to work with is the magnetic force on a current carrying wire. So this is, you'll see it written two different ways again. One's the calculus version and one is the algebra version. And so this is ILB, once again sine theta. So this is the magnetic force on a current carrying wire. So we're going to illustrate, those are going to be the first two. The force on a particle, force on a wire will be the first two we do. So let's go on and do some of those. And let's look at some problems, and then I'll come back and do the next set. I'll do the next set, I guess, on the next video. I'll kind of break this up into pieces, so it'll be a little bit more bite-sized. So if we look at, let's look at number 7. Number 7 says you have an ion with charge Q, mass m, and speed v, enters a magnetic field B and deflected into a path with radius curvature r. If a second ion has speed 2v, we don't change the mass of the particle, we don't change its amount of charge, we don't change the amount of magnetism, what will the radius be for the second one? Well, here's what we've got working here. They tell us it goes into a magnetic field and it curves into a curved path. So we don't know what the path looks like, but it's coming in and it's curving like so. So to do a little physics 1 with you, that means that this particle is experiencing a centripetal force. And the centripetal force, this formula is the only one that you use on the test that is not actually written on the test. They put that acceleration centripetal is v squared over r, and they expect you to remember that force equals ma, which is also on the sheet. So that you have these two equations, but they go together to make centripetal force. So since it's moving in a circle, we have this piece. We also know that the reason it is moving in a circle is because of the force magnetic makes it move in a circle. So force magnetic is QVB sine theta, and I'll talk about how the angle comes in, and this is mv squared over r. Now, we're assuming, and I'm just going to guess, we're going to take a particle and its velocity, so the particle is out here, it's got some amount of mass and it's got some speed, but when it came in here, we're having to use our right hand rule. So in this case, my palm would be into the paper and my fingers would be to the right if I assume this is a positively charged particle. If that is the case, the force on the particle will be up. So the force will go up. And the angle between the velocity vector and my thumb are 90 degrees. So this is sine of 90 degrees. Almost every problem you work with is going to have a sine of 90 degrees. So we know that Q is some number, and V is some number, and B is some number. So this is our original setup. This is our original value. And when we do that, we get mv squared over capital R. So you may remember from Physics 1 that we do a lot of formula manipulation. So here's our new values, and let's see what changes. So our new value is we are going to double the speed. So now we have Q 2v b sine 90. Sorry, we got some interruption there. And so now what I want to know is what is the new velocity. What happens to our velocity when I fill it in here? Okay, so what's going to happen? Well, on this side we have doubled 2 times the force magnetic. So the force magnetic side has doubled. So what does that do on the other side when we don't change anything else? Well, we've got on this side we have m, but 2v squared. Yeah. Sorry, real life gets interrupted. So on this side we've gone up by twice as much, but on this side we're trying to solve for r. Okay, so now on top we have 4v squared over r, and over here we have 2qvb sine 90. Now, to save myself some time, this is 2qvb. Sine of 90 equals 1. This side is 4mv squared over r. So in the first scenario, I have QVB equals mv squared over r. So r equals mv squared over QVB. Both of those are 1s. But now when I do this, I get 4mv squared over 2QVB. And 4 over 2 reduces to 2 over 1. So my new radius must need to be twice as big as the last one. So our correct answer on number 7 would be B. That if we double the speed, we actually double the radius path. So this new particle coming in will make a much bigger radius circle. Okay, so that's number 7. Let's do another one. All right. That's not one we want. There's some more. Okay, so let's look at number 16. And number 16 is going to ask us, 2 parallel wires are carrying different electric current in the same direction as shown. How does the magnitude of force of A from B compared to B to A? Well, this question is actually not about the amount at all. It's when A pushes on B, how hard does B push on A? Now, I know we hammered that last year. So by Newton's third law, force from A to B is exactly the same size as the force from B onto A, but it points in the opposite direction. Since they only ask you for how does the magnitude, the amount, we're going to ignore that little minus sign right there, and they will be equal. So our answer here is D. But what if we altered this question just a bit? What if I wanted to know what force does A have on B? Well, it depends. There's 2 formulas here, and we have, do we have a wire or do we have a wire segment? If we have a wire segment, we're going to use I for current. Magnetic force will be I for current, L for length of the segment, and B. So current, length, and magnetic field strength will tell us, so this is your magnetic field, will tell us. In this case, we've got 2 parallel wires that are carrying, they're carrying current. So what we're going to look at is A to B. If this is like an infinitely long wire or a really long wire, the magnetic field around it, when we do our thumb rule, just so you know, if we have our current going this way like the picture shows, my thumb will lay across here and my fingers will wrap around here so that we have our thumb to the right and our fingers wrap around the top. So we've got coming out at you on top, going into you on bottom, and so our magnetic field goes around the wire. So in this case, we just need to know how close to the wire we are. So what we're going to do is we're going to use mu sub naught I over 2 pi r. And that is going to be the amount of magnetic field you get. Now, if we go back to our formula sheet, and I'm going to do that for just a second. Where is my formula sheet? There we go. When we look at my formula sheet, you will see this formula given as magnetic field strength. So here's your magnetic field strength. If you have a current, so this is magnetic field strength from a wire. Okay, so the wire creates a magnetic field, and then the magnetic field creates a force. Okay, so magnetic field, wire, current carrying wire with current running in it, produces a magnetic field around it. Then that magnetic field is going to produce a force. So let's start with that. Let's find this piece. So for our first part, the magnetic field strength is just the 4 pi times 10 to the negative 7th, that's our constant. The current in our wire, they told us, was I, and 2 times pi times the radius. Now, I want to talk about this. We don't have numbers in this problem, so I want to talk about a couple of things. The reason we write this constant like this is because it allows me to cancel out and leave me 2. So I have 2 times 10 to the negative 7th times current over radius. So what do I know about the force here? What do I know about the field strength? More current means bigger field. More radius, further away, more radius means field goes down. So just like electricity, the closer you are, the more you feel the force. The further you are, the less you feel the force. Sorry, you guys are getting a lecture that's interrupted all the time. So what we've got here is, if we have wires, and this is what I wanted you to get the big picture, because I know that we're not doing this, we're not having a lot of time to review it, it's going to be okay. But the big picture is the magnetic field. Since these magnetic field lines are circles around the wire, as you go further out, the magnetic field strength gets weaker. But you can have a lot of current running in a wire, like one of those high voltage wires that we send out from the power stations to homes. That's a high current wire. And so that high current wire will make a large magnetic field around it, and so that will affect the region more strongly. So the formulas here, you use them as you need them, but to understand them, make sure you understand what the big picture is. If I is in the numerator, then when I gets bigger, magnetic field gets bigger. R is in the denominator, so if R increases, magnetic field strength decreases. So I'm going to do one with actual numbers here that is very similar to number 16, but I'm going to put some numbers in. So let's go ahead and do that. Let's say that the current, that I equals 0.05 amps, which would mean that, so that's for A, and the current for B is going to be 4 times that. So it's going to be 0.20 amps. By the way, current in A would not kill you, current in B could. It's real close to what the cutoff is for your body to be able to handle. Sorry. It's way big. This would kill you for sure. Never mind. I was thinking 0.02, not 0.2. So when we want to know, let's say that I have these 2 wires, and I have a charged particle here. Let's make it a proton. And the proton is 3 millimeters away from the top wire. So this would be a free response. What is the magnetic field strength at that point? At the point. And then our second question to ourselves is going to be, okay, what is the force on the particle at that point? What is the force? So let's start with, we're bringing a proton in, so we're going to be moving this way, and let's make it slow, 1 meter per second, just to keep it easy. So we're going to move a proton in, and we want to see what happens when it gets in the magnetic field. Well, the first thing that we need to know is, what is the magnetic field? So the magnetic field from this guy is, let's make this in here 3 millimeters as well. So we've got here to here is 6 millimeters, and then another 3 on the other side. So we've got how far is the center of this wire to the particle. So we're going to use the magnetic field from the 4 current wire plus magnetic field from the 1 current wire is going to be our total magnetic field. So here we go. Mu sub naught I, which is 0.20, over 2 times pi times the radius, which is 3 millimeters, except that that's not the radius for this one. The 4I is 6 millimeters away. So 6 times 10 to the negative 6, that's our first one. And then once again, our formula is mu sub naught I over 2 pi r. So for the smaller wire, the smaller current carrying wire, we have mu sub naught times 0.05 all over 2 times pi times 3 times 10 to the negative third. And so our magnetic field strength is going to equal that all added together. Now I'm going to need a calculator to do that, and I'll put in mu sub naught I. So we've got on top so this first one is 6.67 times 10 to the negative sixth, and the other one is going to be similar to that, and that one's going to be 3.33 times 10 to the negative sixth. So our magnetic field strength is going to be 1 times 10 to the negative fifth because of round off. So this is in Teslas is our unit. So our magnetic field strength is 1 times 10 to the fifth. That's a pretty normal field strength for most current carrying wires, and it's in the neighborhood of about the same strength as an electric field. So now, what is the force on the particle? Well, here's the force on the particle. Force on the particle is Q times V times B times the sine of the angle, and the angle is between your velocity and your magnetic field. So your magnetic field comes, in this case, currents to the right. Your magnetic field is coming out of the page and into the page, out of the page and into the page. And so the magnetic field comes out of the page while your thumb, so here's where our thumb is. Our thumb is this way, but our current carrying wire, the magnetic field, is coming at a right angle. So here to here is a right angle, so that sine is 90. So then all we have is a proton has a charge of 1.6 times 10 to the negative 19th. That as well as on your formula sheet. V is the speed, so I just made that 1, and the magnetic field strength is 1 times 10 to the fifth. So this proton will experience a force of 1.6 times 10 to the 14th, negative 14th, and that would be in newtons. So those are how those two rules work. One is to find the field strength, one is to find the force of. Okay, so that's our first video. We're going to stop there and we'll post that one. And then I'm going to do another one on the electromagnetic induction part. So we'll stop here for this.